Today's lecture is going to be about random variables. So now we've really gotten into the meat of the probability course. And this is kind of where things start to get really interesting. We start talking about random variables. So we should start off today's lecture with an example. And my example is going to illustrate what a random variable is. And the kind of main idea behind random variables is we'd like to move away from talking about probabilities purely in terms of sample spaces and events. Those are the important underpinnings of everything we're going to do henceforth in this course. Kind of the axiomatic building of probability depends on all of that, and all the basic theorems depend on all of that. But what we would like to do is kind of build up an algebra of ways to talk about probability. And the way we do that, normally in mathematics we have variables, but now we're going to introduce what we call random variables, which are going to kind of give us some of the kind of nice algebraic manipulations we can do and we want to do in a rigorous way. That rigor is going to be built upon that foundation of sample spaces, events, etc. So let's start off and let's talk about what a random variable is. And here I'm going to consider maybe my favorite example here. And my example is going to be that I'm going to flip a coin 3 times. And what I want to do is I'm going to define a random variable. And a random variable is simply going to be a summary of an outcome. So I might define a random variable, and I'm going to define it with what I'm going to call a blackboard bold X. So I'm actually going to draw kind of this second cross on my X is going to be a little more bold. That's going to denote that this is a random variable. That will be very important, we'll see. Anyways, my random variable X, I'm going to define it kind of very colloquially as going to count the number of heads among my 3 rolls. So this is a natural kind of thing to do, right? I can 3 rolls, 3 flips of the coin, right? 3 flips of the coin, right? And this is kind of a natural thing to do. You could imagine this is the kind of things that we want to talk about. We don't want to talk about kind of event level stuff. What we really want to do is say, I want to flip a coin 3 times. I want to count, or I want to summarize my outcome into some kind of variable. So I'm going to count, I'm going to have X, and that's going to denote for whatever my outcome is, how many heads are in the outcome. So what does this look like? I can just draw a table here. Here's going to be my little T table. And here are the possible outcomes, little s's, in my sample space. And what could be my possible outcomes if I flip a coin 3 times? So I could get 3 heads, 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 heads. You know the trick on how to enumerate this? I can say, write heads 4 times, tails 4 times. Then I can start alternating, heads twice, tails twice, heads twice, tails twice, then heads, then tails, heads, heads, tails. Right. So that's just a little kind of binary computer science trick for enumerating my sample space. But all I'm doing here is I'm enumerating my different outcomes. I can get heads, 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 tails, heads, tails, heads, heads, tails, tails, etc. Right? And I'm going to call X, or more properly, I'll denote the dependence on the outcome. I'll write X of S. And X, again, is going to count the number of heads among my 3 flips. So on my first outcome, heads, 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 I would have 3 heads. On my second one, I would have heads, heads, tails, I have 2 heads. On my third one, heads, tails, heads, I also have 2. And I can go through and fill out this table. Here, X, or X of S, to denote its dependence on the outcome, just is going to be my random variable that counts how many heads I get. So heads, tails, tails, I have 1. Tails, heads, heads, 2. 1, 1, 0. So this is what we're going to call a random variable. And the random variable is literally just summarizing. All it's going to do is take outcomes, and it's going to summarize them. Summarize into a number. Because, frankly, we like working with numbers. We don't like working with events or outcomes. We want to kind of do algebra. We want to add things. We want to multiply. And so I'm going to, instead, what we're going to build up over this course is we're going to build up this language called random variables. And a random variable is going to take an outcome. It's going to summarize it into a number. And in this course, we're going to work with real numbers. So you could work with complex too. Let's just stick with real numbers. So what does this look like? It's a table, and it says I have an input, and I output my random variable, which is some feature of my input. So we have an input of a little s, so we have an output of x of s. Input s, output x of s, etc. This is, here, is what we call in mathematics a function. That's all it is. And that's how we're going to rigorously define what a random variable is. Let's go ahead and do that. So let's write a definition. A definition for what rigorously a random variable is. We don't tend to think of it this way, but in an advanced course like this, to build this up properly, you're going to have to think this way. So colloquially, we think of just as a random variable as counting some kind of, or of summarizing in a numeric way some property of our outcomes. But really, our definition of a random variable is that a random variable, and I'm going to really not want to write random variable a bunch of times, so I'm typically going to denote it RV, random variable. A random variable is a function, and that's as complicated as it. A random variable is a function. Of course, I need to give a name to my function. We'll call x, so let's say our random variable x, a function, so maybe I should insert that here. I should say a random variable x is a function, so x is the name of the function, and what is the domain and codomain of my random variable? Well, I take in elements of my sample space, outcomes, and I spit out a number, in this case a real number. So my domain is going to be my sample space S, and my codomain is going to be the real number. So that's our definition of what a random variable is. A random variable is also called, so other ways we're going to refer to this as, sometimes they're called a random variate, or we could say specifically a real valued random variable. In this case, the real valued part refers to the fact that we're outputting real numbers. And in this course, we're only going to work with real valued random variables, and frankly, that's all you really ever need to work with. So I'll probably get in trouble for saying that. Okay. The physicists with this. They like complex random variables. Okay. Another phrase for this would be a univariate random variable. And this will come up much later in the course. The other space we'll work with is we're going to work with, so this is referring to the fact that we're outputting a real number in R, and we're not outputting a number in, say, Rn. Later in the course, we'll work with what's called multivariate random variables, where basically we're going to output in Rn with multiple outputs. So it's often called a univariate random variable, a real valued random variable, a random variate, and we're typically just going to call them RVs for random variable. But a random variable is just a function. It's a function that summarizes our outcomes in S and outputs a number that is a summarizing number. So my example, the summary was it just counts the number of heads. Let's look at some more examples of random variables here. Example. One. Let's say I toss 2 dice, a random variable x. So again, I'm kind of trying to make this bold. I'm trying to make this a bold x without having a type setting. So x, so I'm adding some extra lines here. X, my random variable. I toss 2 dice, but you can think of some. Go pause so you can think of some. Maybe x is the sum of dice, for example. That's a number that summarizes the output. You can imagine a function from the sample space of possible outcomes to the sums of those 2 dice. Other examples, I could toss a coin 25 times, and maybe my random variable x might be the largest chain of consecutive heads. That's a random variable. It's complicated, somewhat complicated random variable, but it is nonetheless a random variable. It's a numeric summary of outcomes that I could observe. Okay. One last example here. I could observe rainfall and let a random variable x be the yield of crops. That's something people are definitely interested in. So that a random. Okay. So the idea with random variables is that we want to build up some kind of algebra so that we can talk about these x's, these random variables here, more in the language that we're used to. So what we like to say, for example, we'd really like to make, and this is where random variables are going to be helpful, make statements like, for example, what is the probability that some random variable x is equal to 1? I'd like to write that. So, if we have a random variable, maybe my random variable back up here is where I flip a coin 3 times. X is the number of heads. What's the probability that x is 1? So we'd like to say the probability that x is 1, for example. And the notation we'd like to use is this. We'd like to write p of x is equal to 1, right? As if x is equal to 1 were an event. The issue is the way we built things up, right? It's a very natural thing to say. Well, if x is the number of heads, what's the probability the number of heads is 1? We want to make that rigorous, of course. 451. Unfortunately, this is really an abusive notation. Unless we're careful, this is abusive of notation. Because if you recall, our probability function was a function from the power set of our sample space to real numbers. I can't plug in, quote, x is equal to 1. I don't really know what that means. Function is equal to a number. Probability of that. What does that mean? We all kind of know what it means, right? What we really mean when we write p of x is equal to 1 is that, again, so if x is equal to the number of heads in 3 coin flips, when we say p x is equal to 1, what we really mean is the probability of a certain event. What's the event? The event that I have exactly one head. Well, we can enumerate that. That would be heads, tails, tails, or tails, heads, tails, or tails, tails, heads. So when we say probability x is equal to 1, what we really mean is the probability of this. Of course, now this is an event properly. And so we could assign a number. In this case, it's what, 3/8. And so there is, in some ways, for at least the simple statement, x is equal to 1, there's a way of making sense of that. There's a way of saying, well, yeah, it's a little bit abusive notation, but we know it. We all know it. What's a little abusive notation among friends? We know what we mean when we say the probability x is equal. We mean the probability of this event, where there's one head. Right? So can we make it a little more rigorous to make that true for whatever kind of statement we want? So what we really mean, the notation x is equal to 1, put this in quotes here, what does it mean? This is, we can say it's shorthand for a certain event. What is the event in shorthand? Well, it's a shorthand for this event, but when we write that in a more systematic way, it's shorthand for all outcomes in S such that when I plug that outcome in X, I get 1. So this x is equal to 1 is really just shorthand for the event of all things, of all events, the event of all outcomes, such that when I plug my outcome in my random variable, which is a function, I get 1. Now that's something we can work with, because this thing, of course, this is a subset of the sample space. It's an event proper. We know how to plug that in the probability function. We know that that's rigorously defined. And if give some people some flashbacks to 214, in particular, this is called the inverse image of 1 under x. So you thought you would get away in probability with not talking about inverse images. You thought you escaped 214. Unfortunately, I'm not going to use them too much, but if you ever have to really think about this, this is the proper way to do that. Okay? And occasionally, and certainly for a course like this, it's good to know exactly what we mean. So this thing is called the inverse image of 1 under x. That is, to say x is equal to 1, we really mean this event. We really mean inverse image of x under 1. Let's do a real quick review of inverse images. So review of inverse images. Review images too, right? So here's our classic picture. I have a set A, and I have a set B, and I have a function that takes elements of A, little a, and maps them to elements of B, let's say little b, and this is f. So in this case, a little bigger, b is f of little a. Okay. So kind of classic function picture, right? So the image of, first we talk about image here. The image of a set, so if I have some set, what do we want to call this set? C, right? So C is a subset of my domain, right? We call this A is the domain. We call B codomain. If C is a subset of A, then if we look at everything that gets mapped to from C over here, so F is going to take all the different elements of C, map them to some set over here. This set over here is called the image of C under F. And often we'll write F of C, right? It's a little bit of abusive notation because really F doesn't take in sets, F takes in elements of A, but it's okay, we know what we mean. So this is called the image. Sometimes it's denoted IM for image of, say, image of C. In this case, we know we're talking about F. Okay, that's image. Inverse image basically goes the other way. So here's our picture. Here is our set A, which is the domain, set B, and I have a function that maps function F, or capital X in our case, function that maps from A to B. If instead here I look at some set, call it D, and so here D is a subset of now my codomain. If I look at kind of the inverse problem, which is to say, okay, if I look at each element of D and I look at what points in A map to it. Now it's possible there's multiple points in A that map to the same point in D, but I look at all points in D and I look and find correspondingly all the points in A that map to D. This set here is called the inverse. Not legible, is it? Inverse image of D under F. And typically we denote this as F inverse of D. Again, a little bit of abusive notation, but inverse functions may or may not exist here, but that's what we do. So just as again, a real quick brief recap here, we can write F of C is every, let's say, little c in B bad way of writing it. It's say x's in B such that there exists a C in big C where F of C is okay, this is called the image. A little bit cumbersome to write. But it's basically all the things in B that get all x's in B that get mapped to by something A. Or, yeah, something in C in this case. That's called the image. And we can have inverse image of a set D, which is actually simpler to write, which is just all A in A, such that when we map it, F of A, actually inverse image, this is called the inverse image. Actually much simpler to write than the image. And so it's the collection of all things, write this, all things in all things in A that map C. And I guess maybe there's a simpler way to write the image. Image is F of X, collection of F of X, such that X is in A. Or X is, I guess in this case, that is C's, X is in C. Yeah, that's probably a simple way of writing it. And it's just all, the image in this case is just all things mapped to by C. And the pictures probably really help here. Image just is everywhere that C goes, and the inverse image is everything that maps C. Image is here, the codomain, and the inverse image is. Okay. If you get lost in that, go review images and inverse. Okay, back to the main point of the lecture here. The main point of the lecture is that notation. We develop these things called random variables. So let's say if I have some random variable x is a random variable, rv, we really want to write, for example, probability that x is in some set A. Here, where A is some subset of the real line, right? We think of x. The reason we're going to do this is we think of x as a number. So random variables allow us to think of kind of algebraically about probability. It allows us to define numbers and think of and treat them, we'll see, as numbers. A bunch of this course is about how you manipulate things and what the rules are for manipulating random variables. We think of x as some kind of number. And so you'd like to say, I have some subset of the real line, maybe x is equal to 1. I want to say, what's the probability that x is in some subset of the real line? You think of x as this random number. And if you take a subset of the real numbers, say, what's the probability x is there, right? And this is abusive, right? Because we can't shove the x's in A into a probability function, right? But we can rigorously define this. We can say that this means the probability of the inverse image of A. Right? And that we know is rigorously defined. So here's the picture. Okay, so sample space and real numbers, and we're going to have a second copy of the real number. Okay. The probability function, typically probability function P maps from the sample space into real numbers. In particular, it maps into set, which is 0 to 1. We can define a random variable, and a random variable, on the other case, maps from the sample space to the real numbers. We'd really like to kind of go directly, last leg, from my random variable x, which we think of as living in the real numbers. We'd like to go kind of directly to probability statements about that. How do we do it? We go backwards. We go through the sample space to R. So first, we go step 1. We look at, if I have some set A over here, and I'd like to say, what's the probability that x ends up in A? First, I'm going to look at x inverse of A. The inverse image is going to be somewhere over here. So this is x inverse of A. And now, this inverse image is an event. We know how to talk about probabilities of event. So we can use my actual probability function, and we could actually make a comment. Oops, this is step 2. We could actually calculate this thing is a subset of the sample space. It's an event. So you could say probability of x inverse of A. Right? That's a valid thing to do. This is a real number. And That's really annoying, cumbersome notation that does not help us think about problems. So what we do, instead of dealing with that, we write this, which is much more intuitive. We write, what's the probability that x ends up in A, right? And we think of x as this random number. What's the probability it ends up in this subset or this subset? A real line. That's what we write. But when you're actually doing the calculations often, and the proper way to link it up to the kind of beginning of this course is, what we actually mean is probability of the event that's the okay. So that's all really kind of abstract. Let's go into a concrete example here again. So this is a bit, this beginning of this lecture is a bit more abstract. It's not as practical in terms of problem solving, but you will need to think of, at least initially, problems this way to actually understand what we're writing down, what we mean. And this is, of course, a math class, and we actually have to rigorously define what we're talking about. Okay. Again, the favorite event, x is the number of heads in 3 tosses of a coin. Okay. And I want to say maybe x equal. What do I really mean by that? I really mean, what's the probability of x inverse of the set containing just 1? Okay. Right, so this is what I'm talking about in inverse images. I'm horribly confusing diagram, but that's exactly what we mean. Let me actually highlight this. This is the important takeaway. Try to draw a picture here. This is important to keep in mind. So when I say probability x is equal to 1, you could alternatively write this as probability that x is in the set containing just 1. What does it mean? That means the probability of the inverse image of the set containing just 1, right? This is really cumbersome notation. That's why we write this. What we actually mean rigorously is this, and we can figure out what the inverse image of this is. And we said before, it's heads, tails, tails. Tails, heads, tails, exactly what you think it would be, or tails, tails, heads, right? We said that's 3 and 8 possibilities, and therefore it's 8 probability. So here's maybe example 1. You could also say, what's the probability that x is equal to 1 or 2? I might write that, right? That's a reasonable way to think about it. So x is the number of heads in the 3 tosses of a coin, right? So you think of it as some random number that could be 1, 2, or 3. 0, 1, 2, or 3. But we don't really know how to calculate rigorously probabilities that way. What we do know how to do is calculate probabilities of events, so we turn this into a specific event. This is the probability that x is in 1, 2. Now, I don't expect you to do this in homework problems, but you need to understand that this is what's happening. And what I really mean by x is in some set is the probability of the inverse image of that set. And now I can look at what the function is. X is a function, right? Remember, it's a random variable. It's a function. And I can figure out what that event is. Inverse image, this is literally all outcomes in my sample space such that when I map that outcome, I'm either equal to 1 or. And of course, we can probably just enumerate these off the top of our heads. Again, it's heads, tails, tails. It's all the outcomes for 1, tails, this tails, heads, tails, 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 heads. Now we have the outcome for 2, which is dot, dot, dot. I think we end up with 6 out of 8 outcomes. So I would pause here. Make sure you understand what's going on in situations. We have to review images and inverse images. Think about what's happening in the mechanics here. A real quick review. So, right, so what we want to do is build up this algebra working with random numbers called random variables. Random variables are just functions. functions that take in elements of our sample space and summarize them into a number. Since we know how to deal with probabilities of events, we're going to know how to deal with probabilities of numbers. So we think of random variables like x as a number, but really behind the scenes, it's a function. And here are some examples of random variables. We'd like to write things like probability x is equal to 1, but we can't plug in that kind of phrase into a probability function. Of course, the probability function really goes from the sample space, or the power set to the real line. So, but really, this is just like saying probability x is equal to 1. It's just shorthand for a certain set. What set is it shorthand for? It's shorthand for the inverse of this of case 1. Review images and inverse images, right? So when you write the probability x is in some set A, your A is a set of real numbers, like 1, 2, 1 and 2, right? So we're thinking of x as some number, even though really it's a function. We're kind of thinking of it as a number that can appear. You can talk about the probability being this set or that set. What we really mean, and I should include this in my. What we really mean here is this probability inverse image of whatever the set is. So our examples are if the set was 1 or 1 and 2. Proper way to account for it. You never actually do this, but kind of the proper way in a more complicated example, find the inverse, whatever the set is, be it 1 or set be 1 and 2. So some other useful terms, and probabilists like to rename things here, so this may be a bit confusing. We can define what probabilists call the support of a random variable. And that's simply a redefinition of the image. So if x here is a random variable, then the support of x is basically, we'll say, quote, is the set of possible values. And right now we're going to say that that is basically the image IM. Or you could write this as x of s. So it's the image. The image of the sample space under, right? X is a function from the sample space. A sample space, real numbers. X is a function. Takes in sample space, outcomes. It's a real number. So you could look at, if I map my whole sample space over the real numbers, what actually is possible? So this is very practical. It seems esoteric, but it's pretty practical. Again, x is number of heads. I can't get all real numbers with number of heads, right? What are my possibilities? Support of x is, again, number of heads in 3 flips. I can get 0, I can get 1, 2, or I can get. It's just a way, a notation for talking about the possible outcome. We call that in probability the support. Yeah. Okay. So notice here that notice if A intersect support x, right? Support is a set, so you can take, you had some set A, and here A, right, better be some event, say an event, that is a subset of the sample space. If you have an event that doesn't overlap with the support, i.e. an event doesn't overlap with the support. Support is all possible outcomes. If my event does not overlap with any of the possible outcomes, what's going to happen? What is the probability that my random variable ends up this? It's going to be 0, right? Because A does not overlap with any possible outcome. So the probability of X ending up in a spot where ending up in part of the real number line that it can't is 0. And this now we actually have the tools to show that this is kind of a trivial little fact. This nice little check that you're following along. The probability of that X is in A is what? It's probability of X inverse image of A under X. And what is the inverse image? Let's draw a picture. If the S, real line, and this is my support, and then I have this thing A over here that doesn't intersect with my support. What is the inverse image of A under X, right? If I have anything in S, it maps into the support by definition. So what things in S map to A? None. This thing, inverse image, is the empty set, which we know by basic rules of probability is has 0 probability. So what we've done is we've made some chain back from talking about random variables being in sets, being kind of in parts of the real line. We made a chain back to the real basic facts we talked about kind of in length. So let's talk now about some more practical aspects of random. So here's a kind of heuristics or rules of thumb. Let's say on types of random variable. And we will make this rigorous. This is not going to be rigorous. So this is informal discussion here. There are a couple of kind of types of random variables people talk about. One would be a discrete random variable. And the second major type being continuous. There's a third type, which is a mixture of the two that we will not talk about. Black sheep of the family, don't want to talk about. So what we call a random variable discrete, basically, if the support is finite or countable. So examples, coin flipping one, let's see, roll, die, and chord, outcome. Support of that is what? The number is 1, 6. Those are my possibilities. Another example might be number of customers arriving at a restaurant. In that case, the support is not finite, but you could maybe say it's the natural numbers. It's still countable. So in those two cases, we kind of call those kind of random variables discrete. This is not particularly formal. We'll maybe at the end of the lecture today talk about formal definition. But this is kind of how people think about it. The number of outcomes is kind of comes in discrete packets, either finite or countable packets, number of them. Call them discrete. a continuous random variable is basically, let's say the support. Yeah, support is uncountably. Again, that's a really heuristic rule of thumb, not particularly formal. But it's how you think about it. For example, example is my random variable is waiting time for a bus. Maybe the support of this random variable is anytime 0 positive, right? It can take on any value in a continuum, so we call them continuous. Not a formal definition, but we'll get to that eventually. But that's kind of how people think about it. These are the two major categories that random variable is typically either discrete or continuous, at least univariate random. That's just kind of something good to have in the back of your mind. Okay. So the first major kind of facet of random variables, thing we can kind of calculate from a random variable, is called the cumulative distribution function. But basically, we're going to spend some time now talking about properties of random variables and ways of understanding what a random variable is and what its properties are. And this will change from random variables. So our first really useful definition called the cumulative distribution almost always denoted CDF of a random variable. Let's write out the definition. If X is a random variable, then the CDF of X is a function going to take in real values, to spit out real values. Function, R to R, it's a real valued function. Nice. Defined, if you give me any little x as an input, f, capital F, typically how the CDF is denoted. CDF is this real valued function. If you give me a little x, real value, then f of x is the probability that my random variable less than or equal. Okay, so let's talk again about notation. So this is why I've been making this bold x. So the bold x this is a random variable with all the meaning that comes with it. Little x is a number. Non-bold for little x is a number. It's a real value number. So the bold x on the left here is a random variable. The little x here is just a number, right? So the cumulative distribution function, CDF, tells me for at each point, what's the probability my random variable is less than or equal to that point. Let's draw a little picture. Here's my real number line. And maybe this is the Lexis. And you can imagine having this kind of half open interval, all values less than and question that my CDF answer that f of little x is the probability by random variable, capital X, notation, straight, is in this. So given some little x, basically my cumulative distribution function is going to answer the question, what's the probability that my random variable is less than or equal to this value? Is somewhere over beyond, less or equal. So this set here is set, we can of course denote as negative infinity x. It includes little x, it doesn't include negative infinity. And so my notation here, when I write capital F for my CDF of little x, just a number, is the probability that random variable x is less than or equal to little x, right? What do I mean by saying the random variable x is less than or equal to little x? Well, I mean it specifically in this half open interval. That probability that x, a random variable, is in this half open interval. And we know what that means now. We know how to interpret the probability that x is in that. Technically the inverse image of the set. So it's a bit notationally heavy. Now you see why we don't write this last one. We write this one up here, or we write this one here. We don't write the last one because that's really notationally cumbersome. But that's what the question is asking. This cumulative distribution function tells us kind of how the probability accumulates up until that point, little x. How much have we accumulated? Let's look at an example. Enough kind of esoteric theory today. So random variables have to happen, but our example, you look at what a CDF looks like, right? So here we go. We toss, same example, right? Toss a coin 3 times, and we say x is the number of heads. And this is kind of how you'd write it in a problem. Now we know that, well, x really is a function, takes in the outcomes and spits out a real number that counts the number of heads, but that's how we think. So what is my CDF? F. What does it look like? Well, what do we know about f? F is a function. Right? F is a function, a real valued function. Like this. So we can draw a plot of it. So let's look at some different values for my plot. First of all, let's look at f of 0. Why not? F of 0 is the probability that the number of heads is less than or equal to 0. Well, what is that? The number of heads is less than or equal to 0. That surely means that it has to be equal to 0, right? Because you can't have less than 0 heads. So this is the same thing as the probability. The number of heads is equal to 0. Well, that's exactly the outcome of just what? Tails, tails, tails. Which is 1 by 8 outcome. So at 0, put 0 here, I have a probability of 1/8. Let's look at another number. Let's say f of 1. So this would be the probability that x less than or equal to 1. So now we could have either 0 heads or 1 head. So I'm going to skip all the intermediate steps, but you're going to get what, 4/8 or 1/2 at this point? I can have 0 heads or 1 heads. 3 ways to get 1 head, 1 way to get 0 heads, so 4 outcomes. So I'm going to jump up 1/2, 1. It's a bit tedious, but It's a nice exercise to go through at least once in your life. What about in between 0 and 1, right? The capital F here is a function. Take it any real number. It doesn't have to be restricted to the sport. It doesn't have to be anything like that. It can be any real number. Well, so example, what if I want to ask about f of 1/2? That's the probability that number of heads is less than or you can't have 1/2 heads. You can't have a third head, right? That is the same thing as asking what's the probability I have 0 heads, right? So if I have less than 1/2 heads, that means the same thing as saying I have 0 or 0, right? That's the same thing as saying what's the probability that I have 0 heads. Because my number of heads comes in kind of discrete packets, 0 or 1. So less than or equal to 1/2 is just the same thing. Yeah, none. And of course, we saw that that's 1/8. And that's actually true for any number between 0 and 1. So I can draw it like this. Any number between 0 and 1, it's just going to kind of revert down to, what's the probability I have less than or equal to 0.8 heads? That's the same thing as saying what's the probability I have 0 heads? I can't have 0.8 heads. So it's all these values are equal to 1/8 until I get to 1. I have this hole where I jump up to 1/2. And I can ask what f of 2 is, which is the probability that I have less than or equal to 2 heads. And that's going to be what, 7/8? And so I would jump up to 7/8 at 2. But any number between 1 and 2, I'm going to similarly be at 1/2, right? What is f of 1.5? Which would be the probability that I have less than or equal to 1.5 heads. I can't have 0.5 heads. That's the same thing as saying what's the probability I have less than or equal to 1 head, which we saw, of course, was 1/2. And so I can play that game for any value between 1 and 2. I would jump up. That would stay at 1/2 until I get to 2 and I jump up, right? And I could ask f of 3, what's the probability I have less than or equal to 3 heads? That is always going to happen. Probability is actually 1 at 3. But between 2 and 3, it's going to stay at 7/8. And any value out here, supposed to line up to 3. Supposed to line up down to any value bigger than 3, I'm going to stay at, right? What's the probability, for example? What would f of 4 be? Probability I have less than or equal to 4 heads. Now that always happens. You can't have more than 4 or more heads if I only have 3 coins. So it just flat lines at 1 up here. And I could similarly ask about numbers less than 0. What would like f of -1? What's the probability I have less than or equal to -1 heads? No, can't happen. So I'm going to, any number less than 0, I'm going to flat line at 0 until I get to 0, and then I jump up. So what we get here is a step function. And where we basically jump up at each value in our support. Notice that this is the support. That's why I picked those values to look at. And this on my y-axis here is my CDF. So if this is x, this is CDF. And that's what it looks like. So for this discrete random variable, my CDF is a step function. Actually, how you define discrete random variable. We'll talk about that later. But in this simple case, it's a nice step function where it increases. And this is actually shows us some general facts that are true of all CDFs. So let's take this example and let's write down the facts, the features of this function that are generally going to be true. Right? So what are those facts? call this a theorem. I'm not going to prove all parts of it, but we're going to talk about some parts of it. Okay. So what are the facts that are true? So if F is a CDF, then fact 1, 0 less than Fx for all x. Fact 1 is that f of x, CDF is always between 0 and 1. That's true. In this case, starts at 0, ends up at 1. And any value in my function is between 0 and 1. Anyone have a proof of that? The proof is actually not so bad. F of x is some probability. I don't even care what it is. But we know that that thing proved has to be. Right, probabilities have to be between 0 and 1. F of x is just some probability. Has to be in 0 to 1. Easy. Nice little fact. I alluded to a second fact here, which is that kind of for high values, x flatlines at 1. And for low values, f flatlines at 1. For low values, f flatlines at 0. And this also is a general fact, which is that f, let's write it this way. Let's write it as some limits. Limit as x goes to infinity is always 1, and limit as x goes to negative infinity is 0. Always ends up at 1 and starts at 0. And what's some intuition for why that happens? We know it's bounded between 0 and 1, but why does it have to start at 0 and end up at 1? Some intuition. I'm not going to do a formal proof of that, although I think I'm going to give you enough tools to prove that. The intuition comes from the third fact. Third fact is that f is non-increasing. Doesn't necessarily have to increase, but it certainly can't decrease. What that means is that if I have two numbers, x1 less than x2, then f of x1 has to be less. So if you believe that fact, we can actually show that one, then it makes sense that it's going to always increase. It doesn't have to strictly be increasing. It's pretty much increasing, right? And it actually is true that bounded between 0 and 1, and so it's going to start at 0 and end up at 1. It's going to always going up, at least never going down. Okay, now here's a clever little proof of it. No tricks at all. It's just going to use some basic facts that we've built up in the lecture today. So here's my x1. x1 is less than some other number x. And you can think of, if I look at f of x1 and I look at f of x2, let's write f of x2 in color. Write f of x2 in red. F of x2 is basically the probability that my random variable lies to the left of x. And f of x1 is basically the probability that my random variable x lies to the left of x1. And so you can look at set negative infinity to x1 and the bigger set negative infinity to x2. Notice that negative infinity to x1 is a subset of negative 2. And so f of x1 is probability x negative infinity to x1. F of x2 is equal to, this way is equal to the probability that x is in negative infinity to x2. And Notice that we have this subset relationship. This means here that one of these is less or equal to the other because one of these things, this one, is a subset of this one. And so we know the probability of x, of whatever, x being in that, is less than or equal to the probability of x being in this one. How do we know that formally, right? You actually have to do the inverse image thing. You have to show that if, so this is formally the probability of the inverse image of this thing. And this one would be the inverse image of this boy, x2. And that, so the sub fact, you have to show that if A is a subset of B, then let's say x inverse of A is a subset of x. So that's a fact. That's kind of a 214 though fact you can show. That's a cute little proof, and it again uses or goes back. The actual way you show these things is you have to go back kind of through the inverse image and all this garbage to the actual basic level of probability, and then it's just a basic probability. Okay, we got 3 facts down. 4th fact is that I can calculate the probability that x is between two numbers, a and b, strictly bigger than a, but not strictly less than, strictly less than a, less than or equal to b. Sorry, strictly bigger than a, x is less than or equal. I can calculate this using my c. It is f of b minus f of a. This is a super cool fact. And the proof kind of is similar-ish to the previous fact, which is that, again, if I have my real line and have some, so here it better be that a is less than, right? Then I have my set here, which is negative infinity to a. I have my kind of bigger set here, negative infinity to b. Then probability a less than x less than equal to b. Right, what does that actually mean? That means that's the probability that x is in set a, b. Like that. Right, it's kind of a half open interval. I could write this as you can justify some of the intermediate steps here, but it's kind of saying that it's basically like the set difference between these. So it's basically like, oh boy, let's do it out. It's basically saying x is in bigger set minus the smaller set. And so you can, I'll let you justify the intermediate steps, but you could say that this probability that x is in negative infinity to b minus the probability that x negative infinity. So some intermediate steps. Justification. And it's not too bad to do that, but you believe from the picture that basically you want to find the probability that x is in this thing, take bigger one and you subtract off the small, right? And of course, this is f of b, smaller one is f. So again, some cute little tricks. Okay. The last fact, which seems a bit esoteric, but is actually pretty important here, is fact 5. is, back to that, f is what we're going to call right continuous. So notice that all of these facts have been true so far for our example up here. So, and these are generally good. Show some kind of sketches. F is what we're going to write continuous. What the hell does that even mean? It means if I look at the limit as x goes to a from the right, look at the limit of f of x as x goes to a from the right, this is always equal to f of a. So recall that our definition of a continuous function, yes, for continuous function, is that the limit x goes to a, let's say a continuous function f, that limit at a is always equal to f of a. The right continuous just means right side. That only a one-sided limit has to actually be. You know, if you need the limit from both sides to be equal. So that's what we call right continuous. What is it practically kind of? How do you draw a picture of it, right? So we noticed that we had this thing that looked like a step function. That was, we had all these jumps in CDF, and this is not continuous. This is not continuous. Okay. Because these two things are not equal. I can take the limit from the left here, and it's not equal to my function value. However, if I come from the right here, and I creep up, I will, this here, black part is f of a, so if this is at a, and if I creep up, this is a limit as x goes to a from the right side, it's going to actually be equal to my function value. So it's not continuous, but right. So that's all it means. It's kind of a weaker form of continuity. You don't actually have a continuous function necessarily, but it is, at least has some weaker continuity. Note, practically, a continuous function is right continuous, right? So continuity is a stronger condition. If you're continuous, you're definitely right continuous. If you're right continuous, not necessarily continuous. Let's say not necessarily vice versa. If you're continuous, then you satisfy this limit from the right and the left. But right continuity is kind of a weaker condition that is satisfied. And the only reason I bring it up is to show up in a theorem. But practically often you just say, well, the CDF is continuous, therefore it's right continuous. Therefore, okay. So these are some facts that we've gone over that are true. And I'm going to highlight a couple of star facts. The star facts are going to be this one. So first we said, yeah, it's a probability, so it's between 0 and 1. We said, actually stronger than that, it starts off at 0 and it ends up at 1. And kind of the related fact is that it's non-decreasing. It never will go down. If we look up at our example, it always goes up. It goes up in steps at some point, but it always goes up. And so it starts at 0, ends up at 1. It's non-decreasing. And then we had this weird kind of right continuity. Yeah, CDFs are right continuous. These facts are always true of CDFs. So what this leads us into is a theorem. And the theorem says that let's say f is a real valued function, right? Like that. F is a function R to R. We then can say f is the CDF of some random variable if following three conditions are held. So above we said if it's a CDF, it satisfies the whole list of those 5 things, right? What we're now going to say is if you give me some random function f, there will be a random variable which has this function as its CDF if the following 3 things are satisfied. So it's a partial converse to the facts above, the exact converse to a couple of the facts. And the facts that have to be satisfied are 3 of those facts. Limit as x goes to negative infinity, 0. Limit as x goes to infinity, 1. So it starts at 0, goes to 1. It's non-decreasing, meaning it's never either increasing or stays the same. And not 2 again. Let's say thing 3 that needs to be satisfied is that f is right continuous. So unfortunately, we have this kind of annoying little technical fact. But again, if f, so f continuous, that's not how you spell continuous. F uncontinuous implies f is right. And that's practically how we're going to use it. So let's look at an example. Let f of x be 1 over 1 plus e to the negative x for all real numbers. That's our f, function, question. So this will often be posed as, is f a valid, put that in scare quotes, CDF? And what people mean when they say is a valid CDF, what they mean is that there is some random variable, we may not know what it is, with f as. So I've given you a function that is this the CDF of some random variable? Well, we have a theorem we can apply. Let's check our 3 conditions. Check. One, the limit as x goes to negative infinity is what? Well, we kind of cheat here. This is if we send x negative infinity, this is like 1 plus e to the negative infinity. So it looks like 1 over 1 plus infinity. This is kind of just good enough for this course, but you have to actually justify this in an analysis. That looks sure like it's going to go to 0, right? And similar kind of thinking, if we send x to infinity, that's like 1 over 1 plus e to the negative infinity. As e goes to negative infinity, this will, as x goes to negative infinity, e to the negative infinity is basically 0. Right? Okay, condition 1, check. Condition 2, f is non-decreasing. How could I justify that? Well, if you know what the graph of f is, but one thing I can do is I can look at f prime of x. This is, I'll let you do the Calc 1 problem. E to the x over 1 plus e to the x squared. This thing is always bigger than 0. So that's okay. That's true, right? If the first derivative is always bigger than 0, it's increasing. This actually shows that f is increasing, which certainly means it's non-decreasing. And right, because e to the negative x is always positive, and whatever in the denominator is squared, always positive. The whole thing is always positive, increase. And the last fact we have to check is right continuous. And I'm going to just say yes, f is, it's a bit hand wavy. We'll check that one off, but this is not going to run into any major issue. This is a continuous function. We're all good. Okay, we're going to end the lecture there, and we'll pick up next time, deep into our exploration of random variables.